Welcome to lecture 17 on continuous functions. We introduce the idea of continuity of a function right after the limits, because if a function is continuous, the calculation of its limit is straightforward. So let's start by introducing, as always, the setting that is going to be a subset D of the real number and a function f defined on D that takes values in R. And let's x0 be an element of the domain of the function. We say that f of x is continuous in x0 if limit of f of x as x goes to x0 is equal to f of x0. So this is the fundamental concept, and this is the reason why if a function is continuous in x0, the limit is easily calculated. In fact, we only need to calculate the function f in x0. We say that f of x is continuous in the entire domain of the function if f of x is continuous for every x that belongs to D. And now we introduce the meta theorem. We will give just the statement of this meta theorem and will rely on it without proving. So the meta theorem says that any function obtained from elementary functions, and when I say elementary functions, I'm thinking about the trigonometric function, exponential, absolute values, and all the functions that we have discussed so far, by composition and or algebraic operations is continuous, except at points where the composition or operations are not defined. Let me give an example of this. If we consider this function, logarithm of 2 plus sine of 3 to the x divided by arc tangent of x plus 5. So let's see what are the elementary functions that we're using now. We are using the exponential function, then we take the sinusoid of this function, and then we combine with the just the plus operation, algebraic operation, with a constant function 2. Then we take the logarithm of all this, and then we divide by the arctangent of x plus 5. Now, assuming that all the elementary functions are continuous, we are obtaining a new function by composition and algebraic operation carried out on these elementary functions. So the meta theorem says that this new function is going to be a continuous, except where these operations are not possible. Now, it turns out that the argument of the logarithm is always positive, so it makes sense to take the logarithm, so the operation is defined. Also, we see that the denominator is arctangent of x plus 5. So as long as x plus 5 is not 0, clearly this operation is also defined. So we can easily now evaluate the limits as x goes to 0, because in fact you see that if x goes to 0, the arctangent, which is another elementary function and therefore it is continuous, this will become arctangent of 5 when x goes to 0. So the denominator is different from 0, so the division is defined as well. In this situation, we can easily calculate the limit by just replacing x equals 0 into this expression. And what we get is logarithm of 2 plus sine of 3 to the 0 divided by the arctangent of 5. And this will be the limit. So let's make an observation at this point. In order to prove the meta theorem, we should prove three things. First, all elementary functions are continuous. Two, the composition of continuous functions is continuous. And three, some product quotient of continuous functions is continuous. Now, we're not going to prove this, but this is what we would need, and we will just rely on this meta theorem many times without proving. Okay, so now that we have an idea of what a continuous function is, of course, most of the functions we will be dealing with are continuous, so it's going to be very easy to calculate the limit. There are, however, still problems when we may have a problem in the definition of the composition or algebraic operation on elementary functions. So in those cases, we need to devise a new method. And the new method that we will devise for evaluating those limits, which are the most interesting cases, is based on some fundamental limits. Okay, so let me introduce now the fundamental limits And these are called the fundamental limits because from them we can derive the calculation of more complex functions, and we will basically build on top of these limits. Now we can classify these limits in three classes. So the first class is what we call parent limits, because they are the most fundamental, and these parent limits are limit of sine of x divided by x as x goes to 0 equal to 1. Notice that sine of x divided by x, if we try to replace x equals 0, of course will give rise to an undeterminate form, 0 over 0. So this is why we need to present this fundamental limit, and we will later on prove that this is indeed the case. The other parent limit is that limit as x goes to plus infinity of 1 plus 1 over x, all raised to the x, is equal to e. Now this limit reminds of the limit of the sequence 1 plus 1 over n, all raised to the n. Of course we will need to prove that this limit evaluated with x as a real variable is just the same, e. Okay, then we have the other class, which is the class of children fundamental limits, meaning that this new class of limits is a consequence of the parent limits, and the children limits are limit as x goes to 0 of 1 minus cosine of x divided by x squared equal to 1 over 2. Then we have limit as x goes to 0 of e to the x minus 1 divided by x equal 1. Then we have limit as x goes to 0 of the logarithm of 1 plus x divided by x equal 1, and then limit as x goes to minus infinity of 1 plus 1 over x to the x equal to e. Notice that this is almost the same of the parent limits, only that now x is going to minus infinity. Finally, we have the grandchildren limits, which of course are just a consequence of the children limits, and we have limit as x goes to 0 of a to the x minus 1 divided by x equal to the logarithm of a for every a larger than 0. Then we have limit as x goes to 0 of tangent of x divided by x equal to the limit as x goes to 0 of arc sine of x divided by x equal to the limit as x goes to 0 of arc tangent of x divided by x, all this equal to 1. And finally, limit as x goes to 0 plus of x logarithm of x equal to 0. And notice that all these limits that we have listed, they are all undeterminate forms. If you try to sub in x the value where x is going to, you always get an undetermined form. Okay, so now that we have these limits, these fundamental limits, and again, we will prove all these fundamental limits in the next lecture, but for now, we just want to learn how to use them. And to use the fundamental limits, let's introduce the change of variables. So the change of variables is just a way of calculating a limit by reshaping, by re-expressing the limits in terms of a new variable, so that we get exactly the same shape of one of the fundamental limits. Rather than giving general definition, just let's start by giving examples, okay? Example 1. For example, let's say that we need to evaluate limit as x goes to 0 of sine of x squared divided by x squared. Now, we don't have this limit in the fundamental limits, but we know that we have this limit. We know that we can try to reformulate the given limit in terms of a new variable. And for example, if we right now that if we set x squared equal to y, clearly we see that when x goes to 0, well, then also y goes to 0. So we can then rewrite this limit as follows. Instead of writing x goes to 0, we can safely write y goes to 0, and now we replace x squared with y and we get sine of y divided by y, but this is exactly the fundamental limit, the first parent fundamental limit, and we know that this is just 1. So that's the idea of change of variables. Let's go with another example. Let's say we need to evaluate the limit as x goes to 0 of sine of 3x divided by 3x. Well, what we can do now is writing limit of, let's say that we have sine of 3x divided by x, okay? And we can rewrite this as limit as x goes to 0 of sine of 3x divided by 3x, and of course we just need now to multiply. So what I'm doing is just dividing and multiply by 3, but now I can immediately recognize that this first part with a change of variable y equal to 3x, we know that this will tend to 1. So the final limit is going to be simply 3. Okay. Example 3. We have the limit as x goes to 0 of e to the sine of x minus 1 divided by x. Notice that each of these is an undetermined form. In fact, in this case, the form is going to be for x that goes to 0, sine of x goes to 0, so we have clearly 0 over 0 here. So we need to do something, and what we would like to do is resorting to one of the fundamental limits, and for example we see that this limit, this children fundamental limits might help. So what we can do is setting is rewriting this as limit x goes to 0 of e to the sine of x minus 1 divided by sine of x, and then having sine of x divided by x, which is basically dividing and multiplied by sine of x. I didn't change anything, but now clearly we see that this first part, by setting y equals sine of x, this will tend to 1, and this is also going to 1, so in the end this limit is equal to 1. Another example is the following. Limit as x goes to 0 of sine of x squared divided by x squared. I'm just trying to calculate in a different way the limit given in example 1. Let's see if there is but let's say that rather than calculating the sine of x squared, let's say that we have the whole thing, the whole numerator raised to the square. This is just like saying limit as x goes to 0 of sine of x divided by x, all this to the square. But because we know that the inner part will go to 1, okay, sine of x divided by x for x that goes to 0 tends to 1, we can easily say that this is just equal to 1 square is equal to 1. Okay, so this is just an application of the meta theorem. Let's pick now a new example, example 5. In this case we have limit as x goes to 0 of cosine of x divided by x. Now in this case what we have, let's see if we have we try to replace x equals 0, what we get? Well, for x that goes to 0, clearly it depends if x is approaching 0 from the positive numbers or from the negative numbers. In fact, in this case what happens is that if we approach 0 from the positive numbers, cosine of x will become a small positive number, which divided by a positive number will give rise to plus infinity. If instead we approach 0 from the left hand side, well, we have cosine of x, which is always positive, but at the same time x is negative, so this will become something like this. So clearly we don't have any limit, so this has no limit. So we are falling now into one example of case 4. So this part of the graph corresponds to limit as x goes to 0 plus of cosine of x divided by x and is plus infinity. This part of the graph corresponds to x approaching 0 minus of cosine of x divided by x and goes to minus infinity. So this is a situation where the two limits approaching 0 from the right or from the left are different, so clearly in this case there is no limit. Let's go now to another example, example 6. Let's consider the limit as x goes to 0 of sine of cosine of x divided by cosine of x. Once again, we have an undeterminate form because when x goes to 0, cosine of x, well, actually no, in this case we realize that when x goes to 0, cosine of x, this will tend to 1 and this will tend to 1. So in this case we simply can evaluate this limit by just using the fact that this function is continuous. So we can say that, let me use the green now, the function sine of y divided by y is continuous in y equal 1. So in other words, we can just set the limit, set the cosine of x to be equal to y, and clearly we see that if x goes to 0, y goes to 1. So this limit basically becomes the limit as y goes to 1 of sine of y divided by y, but this limit is simply equal to 1. Another example, example 7. Let's consider now the limit as x goes to 0 of logarithm of 1 plus sine of x divided by arc tangent of 2x. And now we have an undeterminate form because this will become logarithm of 1 divided by arc tangent of 0, which is clearly 0 over 0. So this is an undeterminate form. But we can rewrite this limit as x goes to 0 of going back to the fundamental limits. We know that in the children limits we had this limit of logarithm of 1 plus x divided by x if x goes to 0. So we would like now to somehow obtain this numerator with x that goes to 0. How can we do this? Well, there is a simple trick. Simply, we know that sine of x is going to 0, so we can keep logarithm of 1 plus sine of x divided by sine of x, and we see that if we just set y equal to sine of x, we know that this limit is going to be 1. Okay, so we have now sine of x, we need to multiply by sine of x, and if we divide by sine of x, we have another limit that we know is gonna tend to 1, but still we have arc tangent of 2x, so we might need to have another fraction that is 2x divided by arc tangent of 2x, and this will be another limit that by just taking y equal to 2x, this will tend to 1 as well, and we need to add 1/2 here to recover the original limit, because clearly you see that if we simplify this expression, this will go away with this will go away with this, and this will go away with this, and if we just remove the yellow part, you see that we are back to the original limit. Logarithm of 1 plus sine of x divided by arctangent of 2x. So clearly the right hand side is equivalent to the left hand side, but now because of all these limits, fundamental limits, we can say that this is just equal to 1 divided by 2. Okay, so let's move to a new example, example 8. Let's consider now the limit as x goes to 0 of logarithm of cosine of x divided by x to the square. And let's see if we can evaluate this just using the continuity of the function, but we see that this is clearly will have 0 at the denominator and 0 at the numerator, because the logarithm of 1 is 0. So we cannot just apply the meta theorem. We need to rely on extracting some fundamental limits from this. How can we do this? Well, we can rewrite limit as x goes to 0. Remember the limit, remember this limit. These fundamental limits, once again, these fundamental limits, right, the one that is using logarithm of 1 plus x when x goes to 0, we need to re-express this in a similar form, and there is a simple trick we can use. We can rewrite the numerator as logarithm of 1 plus cosine of x minus 1, and now we see that this expression is something that will tend to 0 as x goes to 0, okay, because cosine of x will tend to 1 minus 1 will go to 0. So we would like now to have at the denominator exactly the same quantity, cosine of x minus 1, and then of course we need to multiply once again by cosine of x minus 1 and leave x squared here at the denominator. And we see now, let me just copy this below. Right, so we are saying that this is equal to that, but we see that this is now, by setting y equal to the cosine of x minus 1, this will converge to 1 by one of the fundamental limits, and instead this will converge to minus 1/2. We are just using, in this case, the fundamental limits, namely these fundamental limits, just using a minus in front to change the sign of the numerator. So yes, we can conclude that this limit is equal to minus 1/2. Let's do another example, example 9. Now let's make an assumption, and we will prove this assumption later. Okay, so assume that the limit as x goes to plus infinity of the ratio between the exponential a to the x and x to the b is equal to plus infinity for every uh, uh, a larger than 1. So we have an exponential at the numerator, and we have at the denominator just a power, okay, for every b larger than 0. Remember that we proved a similar result for the sequences, okay? But now we should prove that this result is equally valid if x is a real number rather than just a natural number. Let's assume this, and we will prove this later. But if this is true, we can now try to solve to calculate this limit of for x that goes to plus infinity of logarithm of x divided by square root of x. And we will prove now that this limit is equal to 0, which is just like saying that basically the power at the denominator is just a power with a fractional exponent. The power wins over the logarithm. Now, how can we prove this? So the proof is the following. We can say that if we, in the previous limit, if we set y equal to the logarithm of x, now it happens that if x goes to plus infinity, well, also y goes to plus infinity. So the limit then becomes limit as y goes to plus infinity of y divided by the square root of e to the y, because clearly if from this, of course, if we raise both sides, if we apply the exponential, we have e to the y equal to the e to the logarithm of x, which turns out to be exactly x. So we can just replace x with e to the y, and we can also rewrite this as the limit as y goes to plus infinity of y divided by square root of e, which is just a number, raise it to the y. So we are saying now that because the power wins over because basically we have an exponential here, right? So this is an exponential, this is a power, and because the exponential wins over the power, we know that this limit is going to be 0, which proves basically the initial statement, namely the fact that the limit of logarithm divided by the square root of x is equal to 0. Okay. Let's go for one last example of calculation of a limit. Example 10. Let's consider the limit as x goes to plus infinity of the logarithm of 1 plus 3 to the x divided by x. And once again we see that we have an undeterminate form. What is the undeterminate form? Because we have x that goes to infinity at the denominator, right? And also we have an infinity at the numerator, so we have an undeterminate form. Now, first approach could be in line with what we have done before. We might think that we could possibly use one of the fundamental limits with the logarithm. So we could attempt to write limit as x goes to plus infinity of logarithm of 1 plus 3 to the x divided by 3 to the x, and then having 3 to the x divided by x. However, this is not really the logarithm, the fundamental limits we were looking for, because 3 to the x is not going to 0, right? So this is wrong. So we don't know what this limit is, even if we would know that the other limits, because this is an exponential over a power, we know that this will go to plus infinity, but we don't know what the limit is going to be. So we need to devise a new way of solving this. Now, the second way would be just to consider that if x goes to plus infinity, we could say that the logarithm of 1 plus 3 to the x divided by 3 to the x, right? So as x goes to plus infinity, clearly we can neglect the 1 in the argument of the logarithm top. So we could possibly say that this will be something like logarithm of 3 to the x divided by, sorry, this was x, not 3 to the x, right? So this was the original limit, divided by x, but this is simply x times logarithm of 3 divided by x, which turns out to be exactly logarithm of 3. So that's the idea. Okay, so this is the idea for solving the logarithm. So let's provide now the formal proof of this. What will be the formal proof? Well, we can say that the logarithm of 1 plus 3 to the x divided by x, we can rewrite this. We leave x at the denominator, but at the numerator we'll write logarithm of, we factor out 3 to the x. So 3 to the x then multiplies what? 1 plus 1 divided by 3 to the x. And now, applying the properties of the logarithm, we can write this as the x logarithm of 3 plus the logarithm of 1 plus 1 divided by 3 to the x. All this divided by x. And this gives logarithm of 3 plus, then we have the other term is simply x at the denominator, and then we have the logarithm of 1 plus 1 divided by 3 to the x, right? But this second term, this one, this is basically for x that goes to infinity, this will be nothing else that the logarithm of 1 divided by plus infinity, which is clearly 0 divided by plus infinity, which is not an undeterminate form. We know that this is going to be 0, so this finally proves that this limit is given by logarithm of 3.